Okay, welcome everyone. So we are very happy to host Sham Kakade, an alum from Microsoft Research. So he spent 4 years in Microsoft Research New England as a principal research scientist, and now he's a professor in UW, joint CS and statistics, and he will tell us about accelerating stochastic gradient descent.
Great. Excellent. Thanks for Seb for inviting me, and it's always good to be back at MSR. So the question we're going to look at today is, can we speed up stochastic gradient descent? So SGD is one of the most widely used algorithms in practice, and for a variety of reasons, it's used pretty often. It's very simple. It's incremental, and by that I mean, the problem is we want to minimize some function f of x. We're trying to find parameters which make this function value small, and we update these parameters in the direction of some noisy estimate of the gradient. And this algorithm is nice because it's often very easy to cook up noisy estimates of the gradients, and it can often be implemented in a streaming manner. And the streaming is something we're going to be thinking about a fair bit today, because we don't want to hold our whole data set in memory. Okay. So is there a sense in which SGD is optimal, or can we improve upon it? And let's step back a bit and ask this question about gradient descent. So gradient descent is this algorithm where we just follow the exact gradient. Okay, and is there a sense in which gradient descent is optimal, or is there something better? And the answer is resoundingly that there's something much better. And there's something much better both in theory and in practice. So in theory, we have these so-called fast gradient methods like conjugate gradient, heavy ball, acceleration, BFGS. And in practice, if you're in this regime where you can compute the gradient, you would almost always prefer an algorithm like conjugate gradient, because it's literally just as complicated as gradient descent to implement. The same with BFGS. It's like a factor of 2 more memory, and it works. I mean, it's ridiculous how much better it works than gradient descent. So in theory, in practice, there are much better methods than gradient descent for the same sort of memory and complexity.
So when you say better, you're still restricting yourself. You're placing some implicit restrictions on what you allow yourself to do, right?
Yes. So in a sense, in terms of the theory, there's a precise sense in which it's better, and we'll come back to that precise sense. And in practice, it's like, look, we just want something that runs fast. So in practice, better means like everyone would rather do something else, and that's always the case. And they're much happier doing something else for the same complexity. And in theory, there's a precise sense in which gradient descent can be dominated. Okay, and we'll come back to that. Okay, and now the question we're going to look at is basically we're going to sort of review gradient descent, review how we can improve upon it, and then review stochastic gradient descent, and then ask our question. So we're just going to start populating this table. Okay, so the problem is, we want to minimize some function f of x. We're going to review what gradient descent gives us for solving linear systems. We'll review how we can improve upon it. We'll review the stochastic setting, and then we'll try to phrase the question of how much can we improve the stochastic method. Okay, and the punchline for this question is, can we improve it? The short answer is no, and the precise answer is it's sort of no for stupid reasons, and if we're careful, the answer I would argue is a very strong positive yes. So there we go. So no information content on that slide. So the first part, let's just go ahead and review. And throughout, we're going to be looking at the basic problem of solving a linear system, or minimizing a quadratic objective function. And in many settings, like with conjugate gradient, we design an algorithm that's very good for this problem, and it tends to work for a variety of other problems. Okay, and conjugate gradient is one of these algorithms. So this is our problem. We're minimizing a sum of discrepancies in linear equations. So we want to minimize over x. AI is a vector, b is a scalar. Okay, so this is what we're trying to minimize. We're in d dimensions. This is a basic problem. How fast can we solve it? Okay, and n here is typically much bigger than the dimension. Like this is not necessarily a consistent linear system. Okay, so questions about the setting? Okay, so we've got, if n was d, we're trying to solve ax equals b. Okay, and that's not the, and that's why I'm using this notation. In statistics, we'd often have y, w, and x. And here we have like, a is x and b is y. But that's just because I'm using the math notation of solving ax equals b. Okay, so let's review gradient descent. Why is gradient descent slow? Well, it's slow for these problems that are poorly conditioned, which is usually the problems we face in practice. So this is this picture. These are level sets of this function. The trajectory of gradient descent is typically one where it'll quickly make progress in one direction, and then it'll really slow down on this poorly conditioned direction. And the condition number here is really a ratio between how wide this ellipse is to how tall it is. So it's the ratio between the largest and smallest eigenvalues of this matrix determined by A. Okay, so in pictures, that's gradient descent. It behaves poorly when these level sets are poorly shaped. Okay, so in terms of the actual convergence rate, after t, so that's the algorithm, right? Because the gradient of that function, where we write A as a matrix, is just this beast, and this is a problem which is converging linearly. So each time we do an update, we're cutting down our objective function by a constant factor. So it's great in terms of the fact that we're getting linear convergence, but the constant in the rate of linear convergence could be very poor if it's ill-conditioned. So, questions? Yeah.
Are you assuming delta is fixed or?
Delta is fixed. Yeah, you set it to be like 1 over the largest eigenvalue of A, and then so if you set it to be like 1 over like the largest eigenvalue of A, then this is the rate you'll achieve. Okay, and it occur at a geometric rate. Okay, so questions? Okay. Yep.
Where is delta in the word 3?
What's that?
Where is the delta in the class?
The what?
The step size.
Oh, so assuming you set the step size to be 1 over the largest eigenvalue.
So it's like a constant, right?
Yeah, you set it to be a constant. And you don't need to decay it at all because if you're at the right answer, you don't move here.
That's true, but it's too large.
If it's too large, you diverge. So we're setting it to be the correct value here to get this theorem.
Assuming the large system, we do not know the eigenvalue before you.
This is sort of the typical in the literature that assume we set the parameters appropriately. If not, you do a line search.
So that rate actually is big O rate, right?
Well, if you set it to be 1 over lambda max, I think this is exactly the bound, yeah.
I mean, you can get something very slightly.
So just a question of someone who's completely ignorant.
Yeah.
Why would you want to do this instead of just inverting the matrix?
Oh, inverting the okay. So this is a very good question, and we'll go to why. If you're asking this question, then even a more naive question is stochastic gradient descent. Why would we ever even do that? Because that seems like even more stupid than this thing. Okay, so in a sense, we're like going from solving it properly to solving it something that looks bad, and then you go stochastic case, and then this thing looks horrendous. Okay, so inverting the matrix is cubic, or it's matrix multiplication time is the best known. Okay, so this thing, if the condition number is, say, constant or reasonable, the number of updates we need to do to get epsilon accuracy is just log 1 over epsilon. And every time we do this, this is possibly a cheap thing to do in practice, to compute in practice.
Mm-hmm. The gradient.
To get the gradient. So assume, because in many settings, it might be cheap to compute the gradient because it's a vector matrix multiplication. So its order sort of dimension, or n, yeah, it's order dimension. So assume n is about d for this. So it's much cheaper, but if the condition number starts becoming like dimension or super linear in the dimension, then then you might as well do the exact problem. And in a sense, the game here is to try to have the dependence on the condition number as good as possible, because that's the regime where we can beat the exact solution. Okay, and that's sort of why this is critical.
And you would need the pseudo-inverse, right? Not the, because the A is generally not square in your case.
Yeah, but the complexity of that is, if you're solving the linear system, you could, it's pseudo inverses and inverses are the same complexity. They're all the same. I mean, in theory. But we're not going the exact computation, right? We're going kind of the stupid direction of going to stochastic. Okay, so this is just a review of vanilla batch gradient. And now the question is, can we improve upon this? And now we're going to classical results, but let's fill in this table. So after n updates, where we're doing a full gradient computation, which is order sort of dimension computation, this is our error. Okay? And now let's think about, can we improve upon this method? And in a more general sense, naively what you might hope to do is, I'm seeing a bunch of previous gradients. Maybe I could utilize my previous gradients in a more clever way to speed up the convergence. Okay, and there's a sense in which you could ask this question, suppose I'm restricted to live in the span of my previous gradients, which is you're going to be querying for gradients, and the point I'm going to use is going to live in the span of the previous gradients that I've queried. What's the sort of best thing you could do? And there's a precise sense in which this conjugate gradient algorithm is the best thing you could use, but there are sort of a lot of this function is quadratic, yes. So this limits are quite quadratic. There's the heavy ball method, which you can also has similar behavior, and then there's this celebrated result of Nesterov on these accelerated gradients. But they're all methods which try to beat gradient descent by sort of living in the span of the previous gradients. Okay, and it turns out at the same sort of complexity, like the same number of gradient computations, you can really very significantly beat gradient descent. Okay, so I'll show the intuition of the algorithm in a picture, but basically it's kind of like some kind of momentum-ish scheme. But the main point is you can improve the dependence on the condition number to the square root condition number. Okay, and this is massive in practice because your condition number is like 10 to the 4, which is pretty common. It's down to a factor of 100. So you can shave off a factor of 100. And this is, again, sort of bringing up the regime for when these sort of interior pointish methods are competitive with the exact solution. Okay, so conjugate gradient achieves this. So does Nesterov's acceleration. Okay, and the key point is in practice, these methods are really the same computational complexity and memory as gradient descent. So they've they really have the same weight, and they work much better in practice. Yes.
So this accelerated gradient descent, this like an umbrella term for this heavy ball method, and the
No, so I think they're often referred to as like fast gradient methods. So that is what I refer to as the umbrella term. So acceleration typically refers to like Nesterov's scheme, but I think the class I think of them referred to as fast gradient methods.
And the others are providing similar speed ups, or is it?
For the quadratic case, all of them will get this rate up to constant factors.
So they are essentially the same complexity.
Yeah, there's a sense in which conjugate gradient really is magical, in that you could sort of ask like, what's the best polynomial? I think like optimization and math people will say there's a sense in which conjugate gradient really is the best because you can phrase this optimality question more precisely. But if you don't care about constant factors, they're all kind of get this root kappa. And let me just give you a picture of what's going on, because there's tons and tons of proofs of these things. Two of my favorite proofs are, got the experts in the room here. Zeroan has a very nice proof of this, and so does Seb. Different, actually pretty similar viewpoints. But here's kind of what's going to happen in pictures. So with gradient descent, if you start here, you're going to quickly make progress in this. We've got this function that's like this. We're going to quickly fall here and then slowly make progress here. Okay, so we're making a lot of progress in this direction, but not very much progress here. Okay, so what we're going to do with these fast gradient methods, or at least like this acceleration scheme, is we're going to sacrifice progress in this direction to make more progress here. So think about adding like a momentum term. The first step, you're going to really quickly, the first few steps, you're really going to quickly fall into the valley. Okay, gradient descent at this point, you'd be done. You just sort of move slowly here. The fast gradient methods, well, they're going to be like, wait, I'm going to keep my momentum and continue moving up in this direction. Okay, and then I'm going to continue moving up in this direction. I'm going to bounce around and sway into the region. What that's going to do is we're actually losing progress in this direction, but we're making more progress in this direction. Okay, and if you think about it, that's why this analysis is tricky, because this is like this, various game theory arguments and polynomial arguments, but they really are sacrificing progress in some directions to make more progress in the other. You're kind of like putting lots of energy in your system to say go, 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 and you're kind of bouncing around a lot more in these large directions, but the hope is we're still going to get pushed back. But it's delicate, because if we push too much, we'll diverge in this direction. Okay, and we clearly have memory here, because where we move here is not just a function of where we're at. It's a function of the path we got there. Okay, so we are in fact utilizing the previous gradients, and but it turns out you can do this in a way that's not very memory intensive. You don't actually have to remember all the gradients. You can just keep track of like some running averages. Okay, so filling our table in. This is gradient descent. This is the accelerated scheme. You're going to place kappa with root kappa. So both are still linear, but this improvement is very significant, and these algorithms often work extremely well for even non-convex problems. Okay, so now let's go to stochastic gradient descent. So questions about this? This is just a review. Okay, so before we go to stochastic gradient descent, the concern for these methods is they're kind of unstable when you do stuff like this, because you're really, the game is I'm trying to move faster in this direction, and if I used a much larger learning rate, a larger learning rate would be great for making progress in this direction. But if I just did that, I would diverge due to the other direction. So that's why these methods are tricky, because they're somehow trying to effectively use a larger learning rate in some directions, but you have to do this in a way so you don't diverge. Okay, and that leads to, even when you run one of these methods, the pictures seem kind of crazy. Okay, so this is the deterministic simulation. I just got this off someone's blog. The blue line is the performance of gradient descent. This red curve is SGD. So this is iteration. This is log of the function value difference between your function value and the optimal function value. So both are kind of converging linearly, but the rate is much better for the acceleration scheme, but it's not improving the performance at every step. It looks kind of unstable, and as many people try, if you just add a little noise into it, oftentimes it just goes completely haywire, whereas gradient descent is stable.
Sorry, on this slide, the repeating sort of pattern, is that because there's a changing step size, or is this?
No, these are actual constant step sizes for the acceleration scheme. It's really due to this like overshooting business, and
it's actually a sharp. At this point, it's sharp, right?
What's that? Yeah. I mean, just simulating like momentum or something like that, like in a toy example, it's sort of clear that something's bizarre.
What happens there at the bottom when it gets cut?
Oh, this is just 10 to the minus 7, so I just,
Oh, I see.
this really goes down to minus infinity. Yes.
Because the step length is too long, like for this experiment, or
The step lengths are really too long, it wouldn't be converging.
Yeah, the point is like, but these features are pretty generic when you run it, and guaranteeing function value convergence improvements is tricky, as you point out. Right? In a sense, your paper is saying, look, you don't sort of guaranteeing function value convergence at every step is pessimistic. Both of your papers explicitly point out that you should use some other information. So that basically.
plotted something as beautiful as this. So it's
And the fact, so does the blue line eventually go down to zero, or is it bounded below?
No, it'll go down to zero.
But very
Just slowly.
far?
It's still linear, but it's all. But the main point is like these things. They're kind of notoriously unstable in terms of classical numerical analysis. There's a lot of papers when they talk about. If you heard of like Landscher's method, it's basically conjugate gradient for eigenvectors, and any numerical analysis textbook is always like, make sure you have enough bits of precision in memory, or things will go haywire. Okay, and these are sort of deterministic questions. But in a sense, our game is we want to do something quick and dirty. It's going to be noisy. What's going to happen? Like, can we actually get these improvements? And this is a pretty important problem, because in practice we do these very noisy algorithms. And now you're going to ask the question, why would I use an algorithm even worse than gradient descent in practice? Because that alone is not doing the exact solution. And this comes back to the reason that in many of the sort of machine learning problems, we're not sort of doing rocket science or engineering. We're trying to get estimators of things in the world that are fundamentally noisy. So getting the 20th digit of precision in my matrix, who cares if I've only got like 100 samples or something like that? Okay. So maybe we have more than 100 samples, but the point is we don't want numerical accuracy. And the key point is that we never, at least in machine learning, we never care about solving the problem ax minus b, because that's on the data we have. We care about minimizing some unknown objective function. So now we're going to move to that second column. We look at SGD, but the problem there is we don't want to solve the problem ax minus b. We want to solve this problem, where we have a distribution over vectors a and scalars b, and we want to find the minima x. If we knew the distribution, we could state this as, again, a linear system problem. But we're only going to get samples of a and b pairs. So again, this a is a vector, this b is a scalar. I want to find an x which minimizes this. And if I knew the function, this is just a quadratic. Okay, but it isn't. But I don't know the function, so I'm only going to get these sample values. And now the question is, what is how well can we solve this problem? And if we didn't care about computation, this is a statistics problem, okay? But we care about sort of computation as well, okay? And in practice, this is why SGD is very good, because we're going to just do gradient descent, but get some quick and dirty estimates of our gradient, and we're not going to converge to the right answer very quickly. But on the other hand, the fact that it's noisy, there's only a certain amount of accuracy that's justified by our data. Okay, so, but now this is the problem we want to solve, and we're in an oracle model where we can get, say, these A's and B's pairs sampled randomly under the underlying distribution. So questions about the setting? Okay, so now let's look at this algorithm, stochastic gradient descent. Okay, so now we have some parameter x. We're going to update our parameter based on, say, one sample. Okay, so you can just move in the direction of some noisy gradient. Okay, so rather than following the gradient of f, we're going to get some unbiased estimate of the gradient, so an expectation will be correct. Gradient descent for this problem, there's a question of how we adjust the learning rate. Do we turn it down, so on and so forth. But this is a sample of our gradient if we have the current parameter vector xt. Right? This is x minus b times a, so this is a vector. And this is how we update things. Okay, so this is vanilla gradient descent. It turns out there's this really amazing result by Polyak and Juditsky. And it says that if you use a constant learning rate, well, okay, they don't use a constant learning rate, but basically it says if you do gradient descent and you keep track of a running average of your parameters, in the limit, that is statistically the best estimator you could use. Okay, so forget about for a moment the computational problem. Okay, so if I get a bunch of data, there's a question of what's the best statistical estimator, right? And statisticians think about this, and by and large, it's like, take the sample minimizer, right? If I want to measure a bunch of heights, I have like 100,000 people. The best estimator is use the empirical mean on the data I've seen, and that really is there's a strong sense in which that's the minimax estimator. Okay.
Data is Gaussian?
No.
Like general distribution for any distribution.
For any distribution. That's why this result by Polyak and Juditsky is really a limit theorem. They were showing that if you do gradient descent appropriately and keep track of a running average, the distribution of the point you're learning is actually going to be the same as the maximum likelihood estimator, and that's sort of minimax optimal. So it's a very strong, it's not even just you're getting the best rate of convergence, the actual distribution of your estimator matches the distribution of the maximum likelihood estimator.
Like in probability or?
Yeah, probably like almost surely.
Almost surely.
But for the purposes of this talk, forget about the convergence and distribution. If we didn't care about how fast this kicks in, this is a very strong result saying why SGD is such a good estimator, because it says if we have enough data, this quick and dirty thing eventually is going to look like the best statistical estimate. Okay.
So this has the disadvantage of you having to count the number of steps that you made, right?
But the number of steps that you make is your samples, so it's sort of an information theoretic quantity that I have to pass through my data set once, and this says in one pass you're going to get an optimal statistical estimate. Okay, so it's a very strong result. Okay.
Does it assume any distribution on the?
Yeah, basically it's the same kind of assumptions, not necessarily distribution. It's the same kind of assumptions in statistics where you get these kind of M estimator. Basically, whenever you can say the maximum likelihood estimator is optimal, under those assumptions, this thing kind of applies. That's why I can sweep the others under the rug. Yeah.
So you say optimal estimate for something, but for the new.
Okay, so let's be concrete and specialize it to this least squares problem in the special case where the noise is additive. It's more general than this. But suppose the value is b, we see. Suppose this is the true distribution. There's some distribution over b and a, but it satisfies this property. Okay, and we don't know x star. Okay, and this is what we want to minimize. With n samples, the best rate you could get for this problem is the dimension times the noise level of the problem divided by n, with n samples. Okay, and sigma squared is that noise level. This really is the best. Like think about in 1D, what does this say? In 1D it says the rate of convergence is the variance divided by n. Okay, so this is really the limit theorem, and there's nothing better you can do. And having a constant that's much larger than this is terrible, because this constant is real. Like we want the variance in the problem. Okay, so this is statistically the best estimate. If you just do like sort of poor SGD implementations, you won't get this. But if you do the iterative average, then you'll actually get this rate. But there's a question of this little o of 1, and that's kind of critical. Okay. The random samples.
But it's already f. It's already a.
That's right, and that expectation is in f. This expectation is the fact that our samples are noisy. So we're running. So think of like measuring a mean. My amount I'm off from the right answer is the variance over n in expectation. and that expectation with respect to the samples I receive. Right? Because I could, I'm not going to be correct on every path, but in expectation I'm correct, and with stronger, stronger bounds we can say with high probability. Okay? But this is an important point. In expectation, this is the best rate, and this is true for large enough n.
But the noise is fixed. So this noise.
Yeah. This is like just the most bread and butter statistics problem.
Yeah, but can it happen that I look at the same A and B pair once more and get the same noise or different?
The noise is a random variable. So if I look at the same A and if I look at the same A again, I'm going to get a different B, but the difference between B and AX star is sampled from, say, a Gaussian IID. Let's just do the simplified assumption. You can generalize that.
So for the same A, I can get different noises.
You're getting every time you get an A, I'm going to give a new noise and add to it. It's just the vanilla sort of regression model. Robin?
I just sort of remember on the previous slide, the basic here. Okay, so the step sizes are constant, and then your Jazaro averages are moving slower and slower.
Yeah.
But we keep the point moving in the.
Yeah, that's right. That's right.
We don't take decreasing steps there.
Yeah, that's right. That's right. So in the polyhedral I'll give you the precise rate if you keep the constant step size. That seems pretty good. In their results, you actually decreased the step size and did averaging, but for this case, the right algorithm is, use a constant step size and begin averaging some point in time in the future, because you don't want to average right from the beginning. But that's exactly the right intuition. That's sort of keeping your step size large is good because you're really moving in expectation in the right direction, but the averaging says you're going to kind of get rid of the noise. Okay, so let me just give you, so let's just, the short answer is when we think about gradient descent or stochastic gradient descent, there's two parts of the way to think about it. There's, in expectation, we're moving toward the right answer, and there's going to be a part which depends on where we start, the distance between where we start and where we end up, right? Because we start somewhere, and if we start far away from the right answer, it's going to take a long time to get there. Okay, but there's also going to be a part that has to do with the fact that our problem is noisy. Okay, so that you can think of as the variance part. Okay, and if you run gradient descent appropriately, the stochastic gradient descent appropriately, you can get the following convergence rate. Okay, so so after n updates of stochastic gradient descent, and you do an averaging, you get the second term, which is d sigma squared over n, which is great because this is exactly the statistical rate. Okay, then we get this first term, which is kind of looking like we didn't have any noise. It's like this vanilla gradient descent bound. Okay, and this constant kappa has a slightly different definition. So think of kappa here as it's like the analog of the condition number, but for the stochastic case. So for those familiar with the literature, let's do the simplified assumption that say L is an upper bound on how large these vectors are. Okay, so this is also would be relevant like matrix concentration, like how big your vectors are. And let's say mu is the minimal eigenvalue of this E of AA transpose matrix. Okay, and kappa is going to be the ratio of these two quantities. So basically for stochastic gradient descent, there's like a bias part and a variance part. The bias part depends on where you start. Okay, it's dropping exponentially, which is great. But there's this variance part, which is, in a sense, information theoretic. Okay, so this is the bound on sort of stochastic gradient descent. Okay, and so let's fill in this table now. Now we're getting.
So the constant is really 1 in front of the vector. That's the
it's 2 actually for this average scheme dropping constants. I don't know how to drop it from 2 with a constant step size. But we can talk about the constants later on. Okay, so stochastic gradient descent, its behavior looks a lot like gradient descent, but we pick up this extra variance. And of course, this kappa, the definition is a little different. Okay. So, and this is really one of the most widely used algorithms. And the key point is, the statistical part we can improve upon in SGD, but who cares, because that's information theoretic. But there's parts that depend on where we start. And that's what we might hope to improve upon. And now, this question of accelerating SGD, we can think about it is, we still want to get the optimal statistical estimate, but how fast can we kill off the bias? Right? I don't want to somehow improve the bias at the cost of sacrificing variance. Okay, I really want to make this as small as possible. And the naive conjecture is like, look, looking at this table, I'm going to just sort of replace kappa with root kappa. That's sort of what you expect with these fast gradient methods. And that's the naive thing you might hope for. Okay, so the question now is, can we accelerate stochastic gradient descent? Yep.
Will you talk about bounds that do not depend of the sigma mean of h? Like 1 over L over n or L over n?
I won't explicitly talk about that. You can kind of think about what happens if you just like add a little, the smooth case, you just add a little noise. But yeah, formalizing that we haven't done yet, but we know how to kind of think about that setting. Okay. So the real question is, can we beat it? And the root kappa would be amazing if we really could do it, because these algorithms are just much, much better in practice. Right? And SGD, we never use the previous gradients. Well, momentum, we put in a little. In the stochastic case, it's less clear. It isn't clear how much that helps. Okay. So how much, what can we hope for here? Okay. So in terms of, previous results, there's definitely been a lot of work arguing that these fast gradient methods are fundamentally not robust to noise. So there's some work by Nesterov and co. and dAspremont. Again, those are non-statistical. And there's been a lot of work in, somewhat surprisingly, that even Polyak in his book looked at a stochastic version of conjugate gradient with simulations in the 70s and arguing it was unstable. It was unstable to noise. So there's been a fair bit in the numerical analysis literature looking at statistical issues. Lan has some very nice work for accelerating in a different oracle model, but he can't actually explicitly analyze the variance term and show it's optimal. And and there's a string of results more recently for optimizing for better solving the consistent linear system when we have a set of equations. But the real thing is we want to understand the statistics question of what's possible. And just like these old numerical linear algebra questions, like when they ran things, they, Polyak's results and some of the other ones were suggesting this variance term was higher. And that would be sort of disastrous from an estimation perspective. Okay, so the question is, can we find a way to accelerate this thing? And what might that even look like? Because even that isn't known. Like, can we even achieve this root kappa? Okay, so, naively, if you just think about this, the short answer is that this is just not at all possible, just sort of due to stupid reasons. And let's look at one stupid reason. So suppose our A's are standard basis vectors. Okay, so A's are vectors of this form, 0, 0, 1, 0, 0, 0. Okay, so there's a 1 in the ith coordinate. And I'm going to, the distribution is such that you see the ith standard basis vector with probability pi. Okay, so it's not too hard to convince yourself that the condition number of this problem is 1 over p min, because that AA transpose matrix is diagonal, and the diagonals are the probabilities, and that condition number is 1 over p min. Okay, so and gradient descent, kind of needs to run order condition number of steps before anything non-trivial happens. Okay, and you clearly can't beat this because if I don't see all the basis vectors, you can't get a non-trivial statistical estimate. You have to at least wait around until you see all the dimensions, because before that happens, you can't say anything non-trivial. Okay, but once you wait that amount of time, you weighted 1 over p min, so you've weighted an order condition number of samples. Okay, so at that point you could say, look, well, you kind of can't beat this bound because this bound says, look, for something non-trivial to happen, I kind of have to get about kappa samples. And this is just unimprovable. It's not a computation. It's just information theoretic. Okay, so naively, well, we're done. You can't beat SGD. Okay, so replacing kappa with the root kappa would be crazy. Okay,
This is the short answer.
that's the short answer. So let's look at one more example where when you see this, you realize something fishy is going on. So aside from the distribution on the standard basis vectors, another nice distribution to think about is a Gaussian. Suppose A comes from a Gaussian distribution. Okay, so A comes from N0H, because H is the same E of A transpose. Okay, here the condition number is going to be the condition number of the matrix H. Okay, so this is like, we're getting samples from some, say, poorly conditioned ellipse. So you have a Gaussian distribution, that covariance matrix is very poorly conditioned. So you're going to have an example where this condition number is just as bad as the previous problem. Okay, but if you think about this Gaussian example, there's no problem information theoretically. After you see about D samples from the Gaussian, you have a good estimate of what this ellipse looks like. Like, you think of this notion of a spectral approximation, but the point is, get about order D samples from a Gaussian, look what that sort of shape looks like. It basically looks like the underlying distribution. Okay, and that is true regardless of how sort of bad this condition number is. Okay, so for Gaussian, once you get about order D samples, information theoretically, you can definitely start getting good estimates. Okay, but SGD is going to be really bad in this case, because if someone has just measured your coordinates stupidly, they measure in terms of kilometers rather than millimeters or something like that, and you run this algorithm, you're going to get burned. So here, like, information theoretically we're fine, but we're just running this algorithm, say, in some terrible coordinate system. Okay, so in this case, we really might hope to improve upon things, because information theoretically we could do better. And we could just plot these two cases for the behavior of SGD. So this is a log-log plot. So this green curve is sort of this d sigma squared over n. This is what the best information theoretic estimator looks like. It kicks in for this discrete case at around 10 to the 4-ish samples, because that's when you see all the directions. That's when you get a good statistical estimate. And SGD is kind of garbage. But then once you start seeing all the directions, it really starts dropping down very quickly to the green line. Okay, but in this Gaussian case, I set it up exactly with the same condition number. Information theoretically, once you get about 100 samples, because in 100 dimensions, then you have a great information theoretic estimator, because I just solved the linear system exactly. But SGD is taking forever before it starts sort of kicking in, because it's really, it's poorly conditioned. Okay, so this is a case you might hope for improvement, but in the left one, we can't. But in terms of these parameters, they're identical, because the condition number is the same for these problems. Yep.
Just a clarification. The condition number is not the condition number of the covariance matrix. It's something like the trace over the minimum eigenvalue.
Yeah. So
because of B and condition number.
Yeah, that's right. That's right. So kappa for the gradient descent problem would be the sort of the max over min of the matrix. For the stochastic version, it's going to be more exactly. It's going to be more like the sum of the eigenvalues divided by the min. That's exactly right. And in fact, technically, I said it was how it's roughly like how large your vectors are, and that's how large the square norm of your vectors are, which is like the trace. So that's exactly right. So I'm kind of sweeping that distinction under the rug, but that's critical. Yep.
So just a really quick clarification for notation. Small a, is that a particular vector from capital A?
Yeah, small a is a sample from small a is a sample from the underlying. Okay, so we've got this problem, and there's a distribution of vectors a and b, and we're just getting samples of them one at a time. Okay, so we'd like to say we can get an improvement in this case, But in the case on the left, we're basically optimal. So, okay, so now we have to think statistically, because this condition number, the way we've defined it, is coordinate dependent. And we want a notion of how hard the problem statistically is that doesn't depend on coordinates. Okay, and that's like sometimes people call this a leverage score, but let's just define it, and then I'll give the main result. So so now going to your point that the condition number that determines the performance of gradient descent is roughly a bound on how big your vectors are compared to the minimal eigenvalue of that matrix. So for Gaussian, it's something like trace over lambda min. Okay, and this is sort of standard in the sort of optimization literature. Okay, but what determines the sort of statistical complexity, and the way to think about that is how many samples do you need before you get a good approximation to your covariance matrix? So that I mean by you look at your empirical estimate of the covariance matrix, and you want that to be upper and lower bounded by the true covariance matrix. Okay, and basically from these matrix Bernstein sort of arguments, what matters isn't just how big A is in an arbitrary coordinate system, it's how big the vectors A are under the covariance of the problem. Okay, so suppose this thing is bounded by kappa twiddle. Okay. So here I make a hard upper bound assumption. You can relax it in terms of moment properties, but the point is this quantity is invariant to coordinate transformations. And morally for a Gaussian, okay, so technically it's infinity, but it's basically dimension for a Gaussian. Because how big the vectors are under H inverse is the dimension, and you can formalize that. Okay, and how big this quantity is for that discrete distribution is 1 over p min. It's not too hard to convince yourself of that either. Okay, and this quantity, kappa twiddle, is an information theoretic quantity, which is how many samples do you need to get an idea of what that ellipse of your data looks like. And once you get this many samples, you're going to get a good statistical estimate. Okay, so, and for this definition, kappa twiddle is 1 over p min, so is kappa, so they agree. But for the Gaussian case, kappa twiddle is the dimension, and that could be much, much better than the coordinates in your problem. Okay, so now the main result. So those of you familiar with some of these results from sums of finite, optimizing sums of convex functions, like some of the results that Zeyuan has, can kind of guess what we're going to get here. So the improvement now is we can't replace kappa by root kappa, but we can replace it by the kappa times kappa twiddle. Okay, in kappa twiddle, it's sort of easy to see is strictly less than kappa. Okay, so this is a strict improvement, and you can discuss it more offline, but my claim is this really is the right analog of acceleration. For those familiar with these results like root n kappa in the finite sum literature, this is kind of the right improvement here. Okay, and this is a strict improvement. And importantly, we have an algorithm which we don't sacrifice on the statistical rate. Right? So we really get like a constant here for the statistical rate. This isn't some worst case upper bound that's just going to 0. It's you really are getting the right and optimal statistical estimator for your problem, and you're strictly improving upon the bias term. And in terms of the main theorem, what's important about this is an algorithm. You can do this entirely streaming. You don't have to remember any of the past gradients. Its runtime is actually exactly the same as SGD. It's like twice as complicated. Right? So it really is a streaming algorithm. The bias, you strictly improve upon it. The variance is just as good as SGD. And it's a pretty simple algorithm, so I'll come to it in a second.
So accelerated SVRG on the same problem wouldn't give you that?
So there you have to argue about how the finite sum problem relates to the statistical problem, and
It will be the d sigma squared.
No, if n is bigger than kappa twiddle, that's when matrix constant. So first you have to relate for how large your sample size needs to be before it even before you even generalize, and that has to be some multiple of kappa twiddle. Right. So that's sort of the key. And then how do you set epsilon? So you can get this with sort of log n passes through your data set, but then you really have to store everything in memory. And the argument is really about solving your offline problem exactly, and how well does that generalize to the underlying distribution. Right? And in a sense, this is the whole point of Leon Boutou's in those guys' papers. This is why SGD is good and why Polyachevitsky averaging is good, because we shouldn't be going through the kind of numerical version to the statistical version. But I think, in practice, the reason I like these oracles is it's very hard to store things in memory. Even if we store a data set in memory, like if you think of ImageNet or something like that, every time we touch an image, we jitter it. And the same thing with this music data set we've constructed. It really is continuous time, and we're dropping in. That in practice, no one ever, on these large data sets, we rarely store other variables, like we really do want to run in the streaming model. Okay, but this suggests, at least for the square loss case, we can improve upon it, but the algorithm is pretty reasonable. So
what you're saying is that you really are actually sort of in this oracle model. That
Yeah.
there are cases where people are actually implementing something that can take a statistical thing that's never written down anywhere.
Mm-hmm.
Okay.
And I'm saying in practice, on many of these big problems, that really is the case, because when we take, for example, we'll often do some random transformation of it, or like in my music data set, I really am in continuous time. And even though I've stored my whole data set, I'm kind of jumping into a random integer, and we really do run our algorithms, a large class of algorithms are run in this oracle model. So I think it's a helpful abstraction to really work in that oracle model. Just looking at this toy example, we run it, and yes, we're exactly the same in this Bernoulli case. Even just looking at the behavior of the algorithm, we'll come to it, we'll see it's the same. But in this Gaussian case, we get what we expect. Again, this is a log-log plot, so this improvement is pretty significant. It's like a factor of 100, and it's exactly what you might hope for. Well, okay, you'd like to be right here, but we don't know how to do that without doing a matrix inversion. But it does seem to get us right in the geometric mean between where we might hope to be and where we are. Okay? And this is D, that's where we might hope to be. Okay? And, yep.
Is this square root of kappa tilde optimal in any sense, or it's not?
My conjecture is yes. We were sort of arguing about how to write that down with Michael, but to the extent that there are these sums of convex functions where you have this root n kappa, I kind of view that as the analog. I think it'd be a nice question to figure out.
Just because you haven't shown this works in the sum of convex functions case.
Yes, no, I think
gotten this in the
I think that's a great question too. But I think that's So what I'm interested in, okay, so partly I'm interested in theory, but partly like I want algorithms that work in practice that I can really speed up, and it is this weird picture that in the exact land we'll never use gradient descent. Like, it's just completely dominated by LBFGS and conjugate gradient. And in the stochastic land, we have nothing analogous to this aside from momentum. So, part of this was just, I want something that's in practice, that works in practice. And I think it's interesting extending it to other functions, but I think it's also a great question for how do we get things that work well in practice. I won't go through the details of the proof because, part of it is very clean. There's another part which you really have to just understand this as a stochastic process, because that's what, in a sense, SGD is, and you just have to blast that out, and that was pretty hairy. The algorithm is actually pretty cool in that I didn't write this in the paper. We should update the archived version. I think there's a different intuition, which I'll explain now. Suppose we were doing gradient descent. Okay, so gradient descent with a constant step size of 1 over L. That would be like the largest eigenvalue. That would be this update. So forget about this hat. Okay. So suppose I'm doing, like, just getting intuition. I'm doing gradient descent, okay, and I'm using, say, some large learning rate. Sorry, I'm using the learning rate I can use for the exact case. Okay, so now for a moment, suppose you're watching me and you're looking at where I'm going according to gradient descent. And hypothetically, what you're going to do is every time I'm at a place, you're going to look and see where I would have gone had I used a much larger learning rate. Okay, so I'm just doing like vanilla gradient descent, and you're watching me, but instead of like using my learning rate, you're just going to ask yourself, look, if Sham like used a much larger learning rate, where would he have gone? Okay, and I look at this over time. Okay, and let's suppose I just keep track of a running average of where would I have gone had I used a much larger learning rate. Okay, now if I'm running this thing for a while and I run it for like 1,000 steps, and you keep saying, look, every time I'm wanting to move, if I just cranked up my learning rate, I'm getting pushed in the same direction, I should probably be moving in that direction, right? Because somehow, if I'm making progress, my gradients should be going to 0, right? If my gradients seem to consistently keep pointing me in some direction, I probably should be moving in that direction. Okay, the problem is I can't just sort of crank up my learning rate because I'll diverge, but you could somehow, so the idea now is think of like the gradient descent update that's this. What you're going to hypothetically do is think about taking a much larger learning rate at every step. So this is at some step in the past. Consider what happened if we use a much larger learning rate. Okay, and what I'll do is keep track of a running average of what would happen if I had used a much larger learning rate. Okay, and what's that? Meaning where I move to. So this is forget about this. So if I'm at some parameter xt, suppose I add my gradient with a very, very large learning rate. This is just the result of that update.
You do that once for each point you were at the past.
Yeah, each point I'm at the past, I take one step, look where it goes, and I keep track of a running average of where that's pushing me to.
If it's not 0,
Yeah, and the point is like, if this thing isn't the current point I'm at, then chances are like I should be mixing this into my current update. Right, so somehow it's like, suppose I wasn't doing this mixing and you're just watching me and my gradients sort of keep pushing me somewhere else, I probably want to go there. Because if things had been working, my gradients would be 0. So the idea now is to just try to simulate what would happen if I use a large learning rate. So this is just a one-step update if I take a large learning rate. I can't just use the large learning rate because I'll diverge, but I could keep a running average of this and then slowly mix this in. Okay?
So does that require remembering all these values?
You can keep track of it. It's just a running average. So the point is you can update it compactly. So this is like conjugate gradient. You're using the history of all your gradients when you make an update at time t, but you can store this compactly. So what you're keeping track of is, your update is this is the gradient descent update, but we're mixing it in with some kind of running average of where we would have gone in the past had we used much larger learning rates. Okay, but we're decaying it off. And just like conjugate gradient, this momentum is, we're going to be sacrificing in some directions because, look, for some of these directions, I shouldn't be using a learning rate this big because I'm overshooting. But the point is, by doing this running average, yes, I'm overshooting, but I'm going to get pulled back by this guy somehow. So this is why, acceleration is this delicate game that I'm losing progress some directions to improve it on another. And the point is, with noise, it turns out we can show this as noise stable. So we actually use constant learning rates average, and then you just do this log of the arithmetic and it works out. But the algorithm is very sensible.
So did you mean the exponent there to be tau or t minus t? It seems that you're weighting earlier things heavier.
Oh, probably t minus.
No?
Yeah, probably just ignore the math. This is what I'm saying in words. Like I can. Yeah.
Then you have t minus tau.
No, I think it is tau.
No, it's tau. You're discounting values.
I think what you wrote is
all the way
right.
there and-
Okay. Great.
Well, there might be somewhere else.
I don't.
Oh, sorry, maybe it should be tau minus t.
Because beta is between 0 and 1.
Tau minus t. Yeah. At when tau is 0. When tau is 0, this is correct because then I'm mixing in. Then I have the most weight on it.
So it should be tau minus t.
Sorry, the exponent?
No, I think it's.
No, it's not.
No, it's right. When tau is 0, it's the current.
Now T is 0.
I think it's right. Okay, so
By the way, what is YT? Is YT the thing in the bracket?
YT.
YT isn't anywhere.
Hopefully there's no YT.
It's the average of the x's. Return average of YT.
Oh, return the average of xt, sorry.
Oh, it's xt.
Yeah, there's no y's here. So I'm just running this, and then I return the running average of these guys.
Okay.
Yeah.
So you kind of have two things here, right? One is overshooting, right?
Yeah.
Side, and then you have kind of the decaying average.
Yeah.
You know, can you say a little bit what is the role that each one of them play, or are they both?
Yeah. So the reason is that if I just use this large learning rate, some of the directions I'm going to completely overshoot. Like think of this valley. I'm going to completely overshoot in that direction. So I can't use this right now. But the point is, if I overshoot a little, or even a lot, I'll get pulled back by gradient descent. So the point is, it's like what I'm going to do is, overshoot a bit by keep pushing in the direction I want to go, but I'm going to pull myself back for the large directions by gradient descent. And that's why like these acceleration analyses like are super hairy to do. This is because you're actually it really is this argument where you're sacrificing progress in some directions to improve it with other directions. And I can't just use some large learning rate because I really will diverge. And this running average, is kind of the time scale in which I'm going to allow myself to pull myself back from overshooting and speed up in these smaller directions. So the sort of larger the step size I want to use here for these smaller directions, that also means the larger the time scale I'm going to need to use, because I'm going to be.
Is it kind of you're saying I'm going to swing back and forth, right?
Yeah, that's right.
Yeah. So the mu will control how big are my kind of the magnitude of my swing.
Yeah, that's right.
And the beta will control kind of the rate.
Yeah, and the mu we set because if we have some small eigendirection, the flatness, that's like the learning rate I want to use in that direction. This is how much I swing back, but the point is this beta now has to be statistical because it's sort of averaging at a rate in which I see this small direction. Because I don't get exact gradients. So, and the key point is I can always make beta, even if I use some insanely large problem, like I tried this on some deep learning problem, and I used like a learning rate here 10,000 times as big as the one here. And I made it stable by just decaying slowly enough, which I think is great in practice because we need a way to be very aggressive and still make it stable. And this gives us the right parameters to control it.
If we were in exact land,
yes,
then you recover the rate of acceleration?
Yes, we recover the rate of I think the interesting question is, suppose there's no noise and we're solving a set of consistent linear equations. So by no noise, I mean our gradients are still random because I'm only getting kind of rank one, I'm only seeing one equation at a time. Then we're converging geometrically, and that's sort of an in-between case. So, okay, so actually let me just show you the next plot. So this one, I think is very revealing. So now I'm going to assume that B is always AX. Okay, so every time I get an equation, but my entire infinite set of equations has one solution, like a consistent solution. So here you would expect geometric convergence, because if you're at the right answer, you don't move. Okay, and so the sigma squared here is 0. Okay, and the exact algorithms don't work because our updates are rank 1. Okay, and this is a plot of iterations, and this is the log error. What's very interesting here is that, and I think this is very compelling, that this algorithm really is much better because this is the simplest case you can consider. And what was surprising to me is running Nesterov scheme and just vanilla momentum really does beat gradient descent. And momentum we see improves in practice as well. So this is gradient descent. You're converging linearly, and the slope is the condition number. You run momentum or Nesterov scheme, and what's surprising is we did a grid search to find the right parameters, and both were right on top of each other. So momentum and Nesterov scheme were identical, definitely much better than gradient descent. But they're tying two parameters together. Basically, this beta parameter isn't being set right. And this extra degree of freedom means this is this algorithm. And it's really striking, the improvement. And this is not some pathologic example. This is just solving linear, linear equations.
Has anyone tried adding these kinds of extra parameters to momentum for crazier things like deep learning? Because I guess this is a whole bigger family of momentum-y schemes, right?
Yeah. That's exactly the interesting question. I tried this, and okay, this was super toy, and I'm trying to do it more thoroughly because the real question is, you want to be more aggressive, but sort of the kind of $1 million question here is it going to be stable? Because these methods somehow are insane if you think about what's going on. But once I rewrote the equations this way, I felt like it shouldn't be that hard to set the parameters because I can really make this guy some large multiple of this one. But I know I should be able to make the running average consistent because if this is small enough, I'm just mixing in an average of a good point. Right? Because I can basically, for any large learning rate, I can effectively make the running average so slow that it should be stable. And I want to try this out. And it seems super stable. That the way you tune the parameters is first you choose the learning rate for gradient descent, just however you did it before. Then you crank up some large step size, like use maybe like 1,000 times as big or 10,000 times as big. Okay. Now you're going to diverge, and you just crank down your window size till things are stable again. Okay? And this is, so instead of, how do we run SGD? We set the parameters so we don't diverge. And now we just have to do this for two parameters. Okay, and I've been starting to play around with it, and it seems, okay, so the caveat is when I first did this, I thought, well, maybe momentum is just doing this. Okay, and then for a while, I was convinced that we just didn't know how to prove momentum was good. But then Rahul just simulated the thing, and with Praneeth, and we saw a massive difference here, and we're like, no, this really does dominate momentum. Like if it's happening here, and we're doing the grid search, this extra parameter is really crucial here. So I think, in terms of summary and some of the open questions is this acceleration question. I think it really is possible in this stochastic land where we can strictly improve the bias and really get the same optimal statistical variance. And in terms of theory, I think there's an interesting question of, is there lower bounds? There's some analog of like the Chebyshev sort of argument as to what the best you could hope for is for just say solving an infinite set of linear equations where you could just sample them randomly. Okay, and I think the practice one is, so these simulations were, at least the momentum one was in the last week. I think there's a very compelling reason that momentum, momentum and acceleration, it's all kind of the same in the deterministic land. But in the stochastic land, one, it's stable, and two, it's not like we're just saying the old algorithms we had are good. We're actually losing a degree of freedom when we use momentum, and if we add that in, we could actually significantly improve upon using momentum. And the question is, how much do these really help in like non-convex problems as well, or even just broader convex problems? And this is joint work with a number of partners in crime, a bunch of MSR folks that I've been working with for a while, Praneeth and Pratik, who are awesome, and then Aaron, I've been working with these questions for a while, and then the lion's share of the analysis was with a student at UW, Rahul Kadambi, which was really it was really pretty amazing analysis. Like in the sense that it's one of these analyses that once you figure out what's going on, there's no potential function that can analyze this problem cleanly. You really have to understand this as a stochastic process. And like provably we can show that there's no scalar potential function which is sharp enough to do the analysis, whereas these deterministic versions, you can always do the analysis sort of an upper bound on how good, how much progress you've made. But in these settings, you actually have to look at like the full variance covariance matrix of your process. And I think that's very revealing because they aren't just upper bounds. Like their analysis, where we're actually characterizing like the true behavior in a problem-dependent way of our problem. And we can sort of exactly write everything out in terms of fourth moment properties. And by we, like this is basically Rahul. Thanks. Thanks.
Okay, let's take a few questions.
A question from back to slide. Oh, back to the math page, sorry.
This one.
Mu, the hyperparameter, right? Did you guys consider formulating that as actually as a function of tau? The number of, essentially, because that's your step size you're projecting, right? And so essentially, earlier, essentially x t minus tau, the farther back that goes, the farther it is going to be, probably, most likely, right, from your optimal location.
If you do that, you almost only have to make beta also kind of tau. But.
Yeah, I mean, I think in a sense you don't want to because so suppose you're in the linear system and things, you could just adjust this coordinate at that time step. If I want to solve 2x equals 1, for whatever x I'm at, I want to use a learning rate of a half. It's not a function of time. So this mu is basically solving the direction, find me the x such that mu x equals 1. Okay, I always want to use a step size of 1 over mu, and it doesn't matter where x is. For that direction, I would jump to the answer in one step with 1 over mu.
But that's kind of specific to least squares, right? It's not true for... Well, it's true for problems which have sort of generally quadratic growth, but if your problem doesn't, it's not clear that that's true.
Yes, that's right. But in terms of the statistical estimates, yes. So I think there is a question of the more general case for how to do this. But in terms of things like momentum and what we run in practice, like look, this is probably true for momentum too. Yet you just set this as one parameter, regardless of how crazy the problem is.
Did you try exactly this on logistic regression? Does it also accelerate and everything? Or?
I mean, I tried this on MNIST with ReLUs and like 2 levels of ReLUs in there, and it was stable. So, yeah.
Sure.
But I mean, yeah, like asymptotically it will. I think the main question going to practice is I felt like I want to state the algorithm in a way it's clear we can adapt the parameters to make it stable, just like momentum is. And this formulation is very clear to me. It's pretty stable in practice.
You had the chance to basically compare with adaptive learning-based method like added delta or added parallel, like added to see as actually how they actually this method is.
I think Adam, added delta. In a sense, they're incomparable, and my feeling is, in a lot of settings, those methods are really a disaster because they're kind of mixing up two things. That the rate at which you turn down the learning rates, they just get completely wrong because they're just ad hoc turning them down at some rate.
Look at the running average. Actually.
But I'm saying but they that's why they kill you on some vision problems. You're just turning down the learning rates way too fast. Now, in terms of the diagonal scalings, for some problems where we believe the covariance matrix, can be better conditioned in an axis-aligned way, then they're good. That's only some problems, and for those, it's easy enough to run those with momentum or this scheme. But they're really incomparable because, like in a natural language processing problem, I kind of know that my words are special coordinates. And I don't even need to use atom or added delta in these problems. I could literally just scale every coordinate by the variance in it, and that has the same effect. So I think there's a reasonable question of how to combine this with these sort of, I view them as like preconditioner methods, but I think the issue with atom and added delta is they really will kill us on a number of often computer vision problems because they're kind of actually turning down the learning rates too fast. And even just a square loss problems, I've tried it out and it's very clear they're turning down the learning rates too fast. So, but in terms of combining it with them, that it's easy enough to combine momentum methods with preconditioners because you're just using the long steps with the same thing that Adam and Ada Delta are doing.
One reason they actually turn down the learning rate so fast because the number of updates some of the parameter gates is actually so fast, so they have to like add.
But I'm saying like this is false because just look at like a locally quadratic problem, which is often like a reasonable approximation. This is like totally the wrong thing to do. The reason like this really is the wrong thing to do because they're turning the learning rates down way too quickly in those problems. I think the reason they're working isn't so much turning the learning rates down. In fact, they're learning in spite of that. The reason they're working is some features are very rare because they're axis aligned, and they're scaling up the learning rates for those features. And this is something I'm trying to do. Just explicitly understand the curvature in your problems and figure out better ways to do it. But I think separating these two things is actually, it would be a valuable thing to do, but we can chat about it.
Maybe just one last question.
I'll think about it. Okay. All right, let's thank Sham again.